Dear friends, have a good day. Here in this video today we are going to look at introduction of multiple integration. If the given function is function of two or more independent variables, then you can integrate the given function with respect to their independent variables. For example, u is equal to f of x comma y is a given function, then you can integrate u with respect to x and y. When you integrate u with respect to x, keep y as constant, and when you integrate u with respect to y, keep x as constant. Thus, here you can integrate u is equal to f of x comma y with respect to two independent variable. So, this type of integration is called multiple integration. To get a clear idea about multiple integration, have a look at the following example. Double integral over a region A, and A is described as f1 of x less than or equal to y less than or equal to f2 of x, and A less than or equal to x less than or equal to b. So this is x-axis, y-axis, and the shaded region is shown in the diagram. Then double integral over a f of x comma y dA becomes integral over a to b integral over f1 of x to f2 of x f of x comma y dx dy. This is the integral we have to evaluate here. Here this is called inner integral and this is outer integral. Take a look at the limits of the inner integral. Here the limits are variable in x. So first integrate with respect to y, keeping x as constant. So when you do multiple integration, looking at the limit is important. Therefore, the given integral becomes double integral over a f of x comma y dA is equal to integral over a to b integral over f1 of x to f2 of x f of x comma y dx dy is equal to integral over a to b integral over f1 of x to f2 of x f of x comma y dy dx. Here what we have done is we have changed the order of integration because the limit of the innermost integral is in terms of x. So that is why first we have to integrate with respect to y. That is why here we have changed the order as dy and dx. So this is inner integral. Note that the limit of the inner integral is in terms of x. So first we have to integrate with respect to y, keeping x as constant. Suppose the given integral is double integral over a f of x comma y dA is equal to integral over a to b integral over g1 of y to g2 of y f of x comma y dx dy. Here this is inner integral. Have a look at the limit of the inner integral. Here the limit of the inner integral is function of y. So first we have to integrate with respect to x, keeping y as constant. Polar coordinates. Consider the area enclosed by two plane curves r is equal to f1 of theta and r is equal to f2 of theta intersecting in a of r1 comma alpha and b of r2 comma beta. We divide the area into small area by taking lines theta is equal to constant and the circle r is equal to constant. Then the area of the elementary rectangle, which is shown in the figure, shaded area, is r d theta dr. Then the record area is given by a is equal to integral alpha to beta integral f1 of theta to f2 of theta r d theta dr. Here this is the inner integral. This is outer integral. Have a look at the limit of the inner integral. Note that the limit of the inner integral is function of theta. So first we have to integrate with respect to r, keeping theta as constant. Therefore, the record integral becomes a is equal to integral over alpha to beta integral f1 of theta to f2 of theta or d theta dr becomes integral over alpha to beta integral over f1 of theta to f2 of theta or dr d theta. Here the limit of the innermost integral is in terms of theta. That is why first we have to integrate with respect to r. That is why here we have changed the order as dr d theta. This is inner integral. This is outer integral. Now we are going to look at the volume integral. Consider the following triple integral. triple integral over v f of x comma y comma z dv is equal to integral over a to b integral over g1 of x to g2 of x integral over f1 of x comma y to f2 of x comma y f of x comma y comma z dx dy dz. Here this is inner integral, this is intermediate integral, this is outer integral. Take a look at the limits of inner integral. Here the limits are variables in x and y. So first integrate with respect to z, keeping x and y as constant. Take a look at the limits of intermediate integral. Here the limits are variable in x. So secondly integrate with respect to y, keeping x as constants. Take a look at the limit of outer integral. Here the limits are constant a and b. So finally integrate with respect to x. Therefore, the required triple integral becomes triple integral over v f of x comma y comma z dv is equal to integral over a to b integral over g1 of x to g2 of x integral over f1 of x comma y to f2 of x comma y f of x comma y comma z dz dy dx. Here note that this is the inner integral, this is the intermediate integral, this is the outer integral. Here note that the limits of the inner integral is in terms of x and y, that is why first integrate with respect to z, and then the limits of the intermediate integral is in terms of x, so that is why secondly integrate with respect to y, and finally the limits of outer integral is constant, so finally we integrate with respect to x. So first integrate with respect to z, then integrate with respect to y, and finally integrate with respect to x. Now let's take a look at some example problems of double integral. Example 1. Evaluate integral over 0 to 1 integral over 0 to x x squared plus y squared dA, where dA indicates small area in the xy plane. Let us take I be the given integral. So that is why I is equal to integral 0 to 1 integral 0 to x x squared plus y squared dA. Here the limit of the inner integral is in terms of x, so first integrate with respect to y, keeping x as constant. Therefore the given integral becomes integral 0 to 1 integral 0 to x x squared plus y squared dy dx. That is equal to integral 0 to 1. When you integrate with respect to y, keep x as constants, so that is why here x squared is constant and y squared is variable. So if you integrate this, keep x squared as it is, and then integration of dy gives y, and then plus integral of y squared gives y cubed by 3, and then apply the limit 0 to x. So that is equal to integral 0 to 1 x squared y plus y cubed by 3 limit 0 to x into dx. So that is equal to integral 0 to 1, and then in place of y replace x, because x is the upper limit, 0 is the lower limit. First put y is equal to x, the upper limit, and then put y is equal to 0, the lower limit. So then the given integral becomes integral 0 to 1 x squared into in place of y replace x, and then in place of y replace 0. Then what you will get is x minus 0 plus in the term y cubed by 3, 1 by 3 is constant, so take it outside. Then what you will get is y cube, in place of y replace x and then replace 0, then what you will get is x cube minus 0 into keep dx as it is. So that is equal to integral 0 to 1 x squared into x will gives x cube plus 1 by 3 into x cube dx, and then add x cube plus 1 by 3 x cube, then what you will get is 4 by 3 x cube. That is why here you have got integral 0 to 1 4 by 3 x cube dx. Here 4 by 3 is constant, take it outside, and then integrate x cube with respect to dx. Then what you will get is x power 4 by 4, and then apply the limit 0 to 1. So that is equal to 1 by 3 into cancel 4 in the numerator and the denominator. Then what you will get is 1 by 3 into first apply the upper limit, then what you will get is 1 power 4 becomes 1, and then minus apply the lower limit, then 0 power 4 becomes 0. So that is why here we got 1 by 3 into 1 minus 0, that is equal to 1 by 3. Hence, integral 0 to 1, integral 0 to x squared plus y squared dA becomes 1 by 3. Have a look at the example 2. Evaluate double integral over R 4 minus x squared minus y squared dx dy, where R is the region bounded by the straight lines x equal to 0, x equal to 1, y is equal to 0 and y is equal to 3 by 2. First off, let us take I be the given integral. So let I is equal to integral 0 to 3 by 2 integral 0 to 1 4 minus x squared minus y squared dx dy. Here the limits are given as x equal to 0 to x equal to 1, y is equal to 0 to y is equal to 3 by 2. Here note that both the limits are constant, so integrate as per the order given. So here it has been given that the order as dx dy. So first integrate with respect to x keeping y as constant and then integrate with respect to y. So the given integral becomes integral 0 to 3 by 2 into integral 0 to 1 4 minus x squared minus y squared dx dy. So first we are going to integrate with respect to x. So what you will get is integral 0 to 3 by 2 4 into dx gives 4x minus x squared into dx gives x cubed by 3 minus y squared into dx gives y squared into x, and then apply the limits as 0 to 1 and keep dy as it is. So that is equal to integral 0 to 3 by 2, apply the limits, then what you will get is 4 minus 1 by 3 minus y squared into dy. Now integrate with respect to y. 4 into dy gives 4y minus 1 by 3 into dy gives 1 by 3y minus y squared into dy gives y cubed by 3, and then apply the limit as 0 to 3 by 2. First off, apply 3 by 2 in place of y and then minus apply the lower limit in place of y. Then what you will get is 4 into in place of y, here we have replaced 3 by 2 and then minus 1 by 3 into in place of y, here we have put 3 by 2 and then minus in place of y cube, here we have replaced 3 by 2, so that is why here we got 3 by 2 whole cube by 3, and then minus if we put lower limit as 0, then what you will get is the remaining term will vanish. So that is why we got 4 into 3 by 2 minus 1 by 3 into 3 by 2 minus 3 by 2 whole cube divided by 3, and then simplify this, then what you will get is 35 by 8. This is the answer. Then have a look at example 3. Find the area of the cardioid R is equal to A into 1 plus cos theta. For the cardioid, R varies from 0 to A into 1 plus cos theta and theta varies from 0 to pi above the x-axis. Then the required area becomes A is equal to twice integral 0 to pi integral 0 to A into 1 plus cos theta or d theta dr. The required area is shown in the diagram. So here the inner integral is in terms of theta. Note that the limit of the inner integral is in terms of theta. So first integrate with respect to R keeping theta as constant. So that is why here we have 2 into integral 0 to pi integral 0 to A into 1 plus cos theta or dr d theta. Here we have interchanged the order as dr d theta. So this is the inner integral. So that is equal to twice integral 0 to pi and then integration of R gives R squared by 2 and then apply the limits as 0 to A into 1 plus cos theta and then keep d theta as it is. Now apply A into 1 plus cos theta in place of R and then apply 0 in place of R. So that is equal to integral 0 to pi A squared into 1 plus cos theta whole squared d theta. Here 2 in the numerator and the denominators are cancelled. So that is equal to A squared into integral 0 to pi 1 plus cos theta whole squared can be written as 4 cos power 4 theta by 2 into d theta, because 1 plus cos 2 theta can be written as 2 cos squared theta. Here we have 1 plus cos theta. It can be written as 1 plus cos 2 theta by 2. So that is why it will become 2 cos squared theta by 2 whole squared, and therefore we have 4 cos power 4 theta by 2 into d theta. And then put theta by 2 is equal to t, which implies 1 by 2 d theta becomes dt, which implies d theta is equal to 2 dt. and then look at the limits. When theta tends to 0 implies t tends to 0 by 2 is equal to 0, and theta tends to pi, which implies t tends to pi by 2. Therefore, the required integral becomes a squared into integral 0 to pi by 2 4 cos power 4 to 4t into 2 dt. It will become 8 a squared into integral 0 to pi by 2 cos power 4t dt. So with the help of reduction formula, you can write integral 0 to pi by 2 cos power nx dx can be written as n minus 1 by n into n minus 3 by n minus 2 etc. 1 by 2 into pi by 2 when n is c1. Here have a look at the power of cos t. Here it is 4, so that is c1. So that is why apply the first formula. So it will become 8 a squared into 3 by 4 into 1 by 2 into pi by 2. And then simplify this, then what you will get is 3 by 2 pi a squared. Have a look at example 4. Evaluate integral 0 to pi by 2, integral 0 to pi by 2 sin theta plus phi into d theta d phi. Let us take I be the given integral. Here note that both the limits are constant, so integrate as per the order given. So first we have to integrate the inner integral with respect to theta, keeping phi as constant. That is integral 0 to pi by 2, integral 0 to pi by 2 sin of theta plus phi d theta d phi becomes integral 0 to pi by 2 into integral 0 to pi by 2 sin of theta plus phi d theta d phi. So that is equal to integral 0 to pi by 2. Integration of sin theta plus 5 gives minus cos theta plus 5, and then apply the limit as 0 to pi by 2. Keep d phi as it is. So that is equal to integral 0 to pi by 2. Apply the limit pi by 2 in place of theta. Then what you will get is minus cos pi by 2 plus 5, and then plus cos 0 plus 5 into d phi. So that is equal to integral 0 to pi by 2 sin phi plus cos phi d phi. Since cos of pi by 2 plus phi becomes minus sin phi. So that is why here we have integral 0 to pi by 2 sin phi plus cos phi d phi. And then integrate this with respect to phi. Then what you will get is integration of sin phi gives minus cos phi, and integration of cos phi gives sin phi. And then apply the limit as 0 to pi by 2. First apply the upper limit minus cos pi by 2 plus sin pi by 2, and then minus apply the lower limit minus cos 0 plus sin 0. That is equal to cos pi by 2 becomes 0, and then sin pi by 2 becomes 1, and then minus of minus will become plus. So that is why cos 0 becomes 1, and then minus of sin 0 becomes 0. So that is why here we have minus 0, and then the sum becomes 2. Now let's take a look at an example problem of triple integral. Evaluate integral over 0 to 1, integral over 0 to 1 minus x, integral over 0 to 1 minus x minus y, dx dy dz divided by x plus y plus z plus 1 whole cube. Let us take I be the given integral. Here this is inner integral, this is intermediate integral, this is outer integral. Here note that the limit of the inner integral is in terms of x and y, so integrate first with respect to z. The limit of the intermediate integral is in terms of x, so integrate then with respect to y. The limit of the outer integral is constant, so finally integrate with respect to x. So that is equal to integral 0 to 1 into integral 0 to 1 minus x into integral 0 to 1 minus x minus y dz divided by x plus y plus z plus 1 whole cube into dy into dx. Let it be equation number 1. Now we have to integrate the innermost integral with respect to z. Now let us take I1 be the innermost integral. That is, let I1 is equal to integral 0 to 1 minus x minus y dz divided by x plus y plus z plus 1 whole cube. And then this integration will gives x plus y plus z plus 1 whole power minus 3 plus 1 divided by minus 3 plus 1, and then the limit becomes 0 to 1 minus x minus y. And then in place of z replace 1 minus x minus y, and then in place of z replace 0. So that is equal to x plus y plus, in place of z here we have replaced 1 minus x minus y and then plus 1 whole power minus 2 divided by minus 2 and then minus, apply 0 in place of z. Then what you will get is minus of x plus y plus, in place of z we have replaced 0 plus 1 whole power minus 2 divided by minus 2. And then it will becomes minus 1 by 2 into 2 power minus 2 minus of x plus y plus 1 whole power minus 2. That is equal to minus 1 by 2 into 2 power minus 2 will gives 1 by 4 and then minus of x plus y plus 1 whole power minus 2. Therefore, from 1, I is equal to integral 0 to 1, integral 0 to 1 minus x into, in place of the innermost integral, replace the value what we have obtained. That is minus 1 by 2 into 1 by 4 minus of x plus y plus 1 whole power minus 2 into dy dx. Now we have to integrate this with respect to y. So that is equal to minus 1 by 2 into integral 0 to 1, integral 0 to 1 minus x 1 by 4 minus x plus y plus 1 whole power minus 2 into dy dx. Let it be equation number 2. Now let us take I to be the intermediate integral, that is equal to integral 0 to 1 minus x 1 by 4 minus of x plus y plus 1 whole power minus 2 into dy. That is equal to, if we integrate 1 by 4 into dy, then what you will get is 1 by 4 into y, and then integral of x plus y plus 1 whole power minus 2 will gives x plus y plus 1 whole power minus 2 plus 1 divided by minus 2 plus 1, and then apply the limit as 0 to 1 minus x. First off, apply the upper limit 1 minus x in place of y, and then apply the lower limit 0 in place of y. Then what you will get is 1 by 4 into 1 minus x minus of x plus 1 minus x plus 1 whole power minus 1 divided by minus 1, and then minus, apply 0 in place of y. Then what you will get is 1 by 4 into 0 minus of x plus 0 plus 1 whole power minus 1 divided by minus 1, and then it will becomes 1 by 4 into 1 minus x minus of 2 power minus 1 by minus 1 minus of x plus 1 whole power minus 1 by minus 1. That is equal to 1 by 4 into 1 minus x plus 1 by 2 minus of 1 by 1 plus x. Therefore, from 2, I is equal to minus 1 by 2 into integral 0 to 1, 1 by 4 into 1 minus x plus 1 by 2 minus 1 by 1 plus x into dx. Now integrate this with respect to x. Then what you will get is minus 1 by 2 is constant, keep it outside as it is, and then 1 by 4 into integrate 1 minus x, then what you will get is x minus x squared by 2, and then plus 1 by 2 is constant, integration of dx gives x, and then minus integration of 1 by 1 plus x gives log of 1 plus x, and then apply the limit 0 to 1. So that is equal to minus 1 by 2 into 1 by 4 into, apply the upper limit 1 in place of x, then what you will get is 1 minus 1 by 2 plus 1 by 2 into 1 minus log 1 plus 1 becomes log 2, and then minus, apply the lower limit 0 in place of x, then what you will get is 0 plus 0 minus log 1. So that is equal to minus 1 by 2 into 1 by 4 into 1 minus half becomes half, and then plus half minus log 2. The remaining term will vanish. So that is equal to minus 1 by 2 into 5 by 8 minus log 2, and then take minus outside, then what you will get is 1 by 2 into log 2 minus 5 by 8. So this is the required triple integral. If you like this video, share your valuable ideas and comments in the comment box itself. Thank you.